Micro antennas, microstrip antennas, part 2, series on antennas and wave propagation, lecture number 5.17. This is a continuation of part 1 on microstrip antennas. Microstrip antennas are used in microwave communication systems, especially in aviation industry. Certain aspects, preliminary aspects, or fundamental aspects of these antennas are covered in the first part. In the present session, second part, the focus is on feeding methods used with these antennas, along with applications, merits, and demerits of these antennas. Let us start the session by considering certain features which are not covered in part 1. Bandwidth is such a feature. Few points regarding bandwidth of microstrip antennas or patch antennas. There exist several bandwidths and only impedance bandwidth is specified most of the times in case of patch antennas. Also note, in case of patch antennas, the pattern bandwidth is wider than impedance bandwidth. Impedance bandwidth is proportional to the thickness T of the dielectric substrate. Since T is small, bandwidth is also small, typically a few percent. An empirical formula which is appropriate for small values of T over lambda naught for bandwidth is 3.77 multiplied by epsilon r minus 1 by epsilon r square W over L multiplied by epsilon over lambda naught. Here one aspect requires to be mentioned. Patch antennas are associated with so many positive aspects in the form of small size, in the form of conforming to the surface where they are mounted. They are also somewhat cheap to produce, inexpensive. So various aspects are there which are always required, but they are associated with two significant shortcomings. One is their bandwidth is low. They are narrow banded devices. This is one serious drawback. Another drawback is the gain or directivity offered by them is low. So they are low gain devices, small gain devices. These two are serious drawbacks, and of course, certain techniques got developed to overcome these shortcomings. Now, let us move further. Radiation resistance. The radiation resistance of a half wave patch is given by this formula: 90 multiplied by epsilon r square by epsilon r minus 1 L over W square ohms. This is a radiation resistance. Reactance XR is 0. Another feature parameter is effective height. The effective height of patch antenna, in fact any antenna, is this formula under square root 2 R AE over Z naught. Radiation resistance is RR, effective area is AE, Z naught is intrinsic impedance. Here it is given RR is radiation resistance in ohms, AE is effective aperture, lambda square effective aperture in lambda square, and Z naught is intrinsic impedance of the space, ohms. For typical patch antenna, effective height is 30 times as much as it extends above the flat ground plane. So effective height is large. Now, after discussing certain features of certain parameters of patch antennas, we move to feeding techniques that are adopted to give input to patch antennas. Microstrip antennas or patch antennas can be fed by a variety of methods. These methods can be classified into two categories: contact type, non contact type, or contacting type or non contacting type. In the contacting type feed method, the RF power is fed directly to the radiating patch using a connecting element such as a microstrip line. The feed using coaxial line also falls into contacting type category. In a non-contacting scheme, electromagnetic field coupling is done to transfer power between microstrip line and radiating patch. Aperture coupling feed and proximity coupling feed both fall in the category of non-contacting schemes. So it appears contacting type involves direct connection between feed line and the radiating patch. Conducting conductive coupling between feed line and patch, whereas in non-contacting type, the power is fed to the radiating patch through induction. Here it is said aperture coupling feed, proximity coupling feed. These two are examples for non-contacting type. The feed methods are illustrated here. Microstrip line feed. This is microstrip line. This is patch. These are fringe fields. Radiation happens from the fringe field. Input is supplied here. This microstrip line then carries the signal to patch. In B is shown probe feed. Here is a circular microstrip patch. Through a coax, it is fed. Here is connector. It is connected to this connector. Feed line is connected to the connector, and this connector is directly in contact with the patch. So these two are contacting type. Aperture coupled feed. Here is patch. Here is microstrip line. This is microstrip line. Notice here is a slot. So this is the structure of aperture coupled feed. Proximity coupled feed. Microstrip line. This is microstrip line. This is patch. Proximity feeding is given here. A few points. Detailed information regarding feeding methods. The microstrip feed line is a conducting strip with a smaller width compared to the patch. It is easy to fabricate, simple to match. But its disadvantage is with the increase in substrate thickness, the surface waves and spurious feed radiation increase, limiting the bandwidth. So it is associated. Microstrip feed method is associated with limiting the bandwidth. Coaxial line feeds, where the inner conductor of the coax is attached to the radiation patch, while the outer conductor is connected to the ground plane, are also easy to fabricate and match with the low spurious radiation, but they suffer from narrow bandwidths and modeling difficulties. Here, it requires to be mentioned that one should not underestimate modeling difficulties. Difficulty, complexity in modeling means difficulty in predicting the behavior, predicting the characteristics, predicting the properties of the device. So we don't know what polarization it is giving. We don't know what bandwidth it is offering. We don't know the gain given by the device. If modeling is not done, if the device is incapable of being modeled, so it is a serious matter. These two methods suffer with inherent asymmetries, generating higher order modes that give rise to cross polarized radiation. Now, a few points regarding non-contacting type of feeding methods. The aperture coupling feed consists of two substrates separated by a ground plane. On the bottom side of the lower substrate, there is a microstrip feed line whose energy is coupled to the patch through a slot on the ground plane separating the two substrates. So it is through a slot. Aperture is a synonym for slot. Both means the same. It has the advantage of being easy to model with moderate spurious radiation, but is difficult to fabricate and also suffers with narrow bandwidths. Another technique is proximity coupling technique, proximity coupling method. This method is also called as electromagnetic coupling scheme. In this technique, two dielectric substrates are used such that the feed line is in between the two substrates and the radiating patch is on top of upper substrate. The main advantage of proximity coupling feed is it eliminates spurious feed radiation and provides a very high bandwidth, as high as 13%. 13% bandwidth at microwave frequencies is a considerable amount. This is an appreciable aspect pertaining to proximity coupling feed. It is due to overall increase in the thickness of the microstrip patch antenna. This scheme also provides choices between two different dielectric media, one for the patch and one for the feed line to optimize the individual performances. But its fabrication is somewhat difficult because of the two dielectric layers which need proper alignment. Also, there is an increase in the overall thickness of the antenna. Matching can be achieved by controlling the length of the feed line and the width to line ratio of the patch. It appears proximity coupling feed is the best among the four that are considered here. Of course, it is associated with the fabrication difficulties. Now we undertake a comparative study of feeding methods. Four feeding methods we have already covered: microstrip line feed, coaxial feed, aperture coupled feed, proximity coupled feed. When it comes to fabrication, it is easy in case of microstrip line feed. In coaxial feed, soldering and drilling is required. In case of aperture coupled feed, alignment is needed. Proximity coupled feed also requires alignment. So microstrip line feed tops the other methods when it comes to ease of fabrication. In case of spurious feed radiation, in this aspect, microstrip line feed performs poorly. Spurious radiation is large in this feed. It is least in proximity coupled feed. In coaxial feed also it is large. In aperture coupled feed it is low. The microstrip line feed, coaxial feed both suffer with large spurious radiation. When it comes to reliability, microstrip line feed is again at the top. Reliability is better. It is not so good in case of coaxial feed due to soldering. In case of aperture coupled feed and proximity coupled feed, reliability is good. When it comes to impedance matching, it is easy in microstrip line feed, in coaxial feed, in aperture coupled feed, in proximity coupled feed also. Impedance matching is not at all complicated, it is easy. Bandwidth achievable with the impedance matching is 2 to 5% in case of microstrip line feed. Same in case of coaxial feed and aperture coupled feed too. In case of proximity coupled feed, it is 13%. So far, we considered feeding methods to single patch elements or single antennas. Now, we consider feeding arrangements for arrays of patch antennas. It has been told patch antennas give small gain or small directivity. This is true in case of a single patch. Gain can be increased by going for arrays of patches. These arrays, how they are fed, what are the techniques available, those aspects we discuss here. The patch antennas find wide applications as arrays. To feed the elements of patch arrays, two types of feed schemes are used. One is a series feed network, which uses a single line, and other scheme is corporate feed network. Series feed network, corporate feed network. This second one uses multiple lines. Series feed arrays are fabricated conveniently using photolithography for both the radiating elements and the feed network. But this technique is limited to arrays with a fixed beam or those which are scanned by varying the frequency. Even though it can be applied to linear and planar arrays with a single or dual polarization. Another limitation of a series fed is any change in one of the elements or feed lines affects the performance of others. The corporate feed network is used to provide power splits of 2 power n, where n is 2, 4, 8, 16, etc., using either tapered lines or quarter wave impedance transformers. Corporate feed arrays are general and versatile. The designer can exercise more control over the feed of each element, and it is ideal for scanning phased arrays, multi-beam arrays, or shaped beam arrays. Electronic scanning. It becomes easy when we go for corporate feed network. Here is shown array feeding. In A, series feed is illustrated. These are patches. 1, 2, 3, 4. They are fed through this microstrip line series. In B is shown corporate feed. 4 patches are there. Feed, actual signal input is given here. It is split into 2 parts. Again 2 parts, 2 parts. Now we have total 4 parts. These 4 parts are going into 4 patches. This is corporate feed. These two are feed arrangements, microstrip patch arrays. Now another two figures are also illustrated, shown here, appearing here. They are tapered and quarter wave transformer lines to match a 100 ohm patches to a 50 ohm line. Line is 50 ohm. This 50 ohm, 50 ohm, whereas patches are of 100 ohms. These are all 100 ohm patches. How this line is matched to the patches? How the line is connected to the patches? Because simple connection or direct connection between 50 ohm line to 100 ohm patch means lot of impedance mismatch leading to reflections, losses, inefficiency. So one has to design a network through with which impedance match is achieved between the input line and the patch. In A, tapered lines are used to provide matching. You see tapering here. Here also some tapering is there. Here also tapering is there. So these tapered lines are designed. Tapering is selected in such a way that this 50 ohm line is matched to 100 ohm. Another way is through quarter wave transformer. You see here is a quarter wave transformer. Here is quarter wave transformer. Okay. So several quarter wave transformers are used in the network that is interspersed between input line and the patches. Provides matching as well as feeding. Now we consider a few merits of these antennas. These are low profile antennas, conformable to planar as well as non-planar surfaces. So this is biggest advantage, conformability and low profile. These are widely used in high performance aircraft, spacecraft, missile applications where size, weight, cost, and aerodynamic profile are constraints. Microstrip antennas are also used in mobile radio and wireless communication. Main advantages are light in weight and small in overall dimensions, easy manufacturing using printed circuit technology, flush planar technology, aerodynamic characteristics, suitable for aeronautical applications. It can be easily integrated with electronic components, easily integrated into arrays, possibility of printing on curved surfaces to make conformal antenna. These are all advantages. These are associated with the demerits too. What are they? Microstrip antennas suffer with low efficiency, low power, high Q, poor polarization purity, and very narrow frequency bandwidth. Low efficiency, low power. Low power means it implies range, distance of receiving antenna. It cannot be large, small range. Poor polarization purity, small bandwidth, narrow bandwidth is a serious drawback. It has mentioned narrow bandedness and small gains are serious drawbacks pertaining these antennas. Out of these two, the issue of gain can be solved to some extent by going for arrays. By using more number of patch antennas, one can achieve good amount of gain. Bandwidth also, there are techniques they got developed to enhance the bandwidth. Relatively narrow bandwidth in general, except for more complicated geometries, low overall efficiency due to dielectric losses, generation of surface waves at the dielectric and air boundary, and losses in the coplanar feed lines. As already mentioned, it is difficult to obtain high polarization purity. What is this polarization purity? If an antenna is expected to give horizontally polarized wave, and if it gives horizontally polarized wave, then polarization purity is ensured. If it gives other polarizations also, in addition to expected polarization, then purity of polarization is spoiled. Now, a few points regarding applications. They are used in most classical microwave applications, including radars, telecommunications, satellites for television broadcasting, mobile communications, aeronautical applications, space industry, GPS, systems for detection and identification, medical applications, etc. They are giving rise to integrated active antenna arrays. Before going further, it requires to be mentioned here that microstrip antennas or patch antennas can be considered the most modern antennas, and they are pure microwave antennas. They are thoroughly analyzed, and their functioning is completely understood. Various techniques got developed to overcome the shortcomings associated with them. Now they are being employed in the industry, they are being used in the research, they are also being used in a very wide variety of applications. With this, we come to an end of this session. In this session, a few features like bandwidth of patch antennas is considered, along with radiation resistance, effective height. Feeding methods for individual patch antennas and also for arrays are described and illustrated. Applications, merits, demerits are given. Hope this session is useful to you. We meet again, a new topic very soon again.